Welcome to the discussion on the topic of strain energy due to sudden and impact loads. This is part of the chapter strain energy in the course Strength of Materials 1. I am hoping at the end of this particular lecture, at least you are able to get these learning outcomes, differentiation or difference between the strain energy due to gradual and suddenly applied loads. Also, how to compute the strain energy stored in a body due to the impact loads. Right? Let's see first of all how what is strain energy development due to suddenly applied loads. We have already seen gradually applied loads. Let's see the difference here itself. Let's say there is a force acting on a body and the force is gradually applied, right? Its change in the length also gradually increases. Suppose there is a body and I am applying a force, right? I am gradually increasing it, right? Say this is the force and I am gradually increasing it. Then deformation or change in the length also happens gradually, right? Then the strain energy stored, observed, we calculated in the previous session on strain energy, right? The strain energy due to the axial load in terms of load is half times P times delta, right? Half times P times delta or P by 2 times delta, right? That you can refer to the previous discussion on strain energy. Now, when the whole body, when the whole load suddenly acts, here is an example given. The change in the length also taken suddenly, right? So you are applying a load, not a gradual fashion, like increasing, say 1 kilonewton, then putting another load, then putting another load, then putting another load. This is a kind of gradually applied load. So at a time you are applying some 20 or 30 kgs load. Right? The deformation also happens very quickly or suddenly. That is what we are referring as suddenly applied load. For example, there was a load that was hanging from a height on a platform, and it came very close to the platform. Suddenly, the rope was broken, or it broke or it broken. And then what happens? The whole weight of through which the weight is hanging, right? That whole weight will suddenly drop down to the platform. So what happened? Immediately there is a deformation produced in the sudden deformation produced in the platform, right? Now, under such conditions, what is the amount of energy stored? That's what we are going to calculate. So the load may act suddenly. The material, no, the displacement, although the displacement happens suddenly, but the internal resistance in the body, that the body is not prepared, that is not expecting that sudden load will come. So for it, the internal resistance of the body develops gradually only, just like a gradually applied load. When you apply gradual loads, gradually the resistance, internal resistance, energy will be keep building. Right? Same thing happen here also. Although it is a sudden load, right? The material is gradually developing its energy, right, and reaches the maximum. Right? So during the process, we can now calculate what happens. Work done on the body by sudden load is W times, right, delta, right? This is not U, right? It's a delta. So we got the work done on the body as delta, W times delta. It is sudden load. Remember, this is a suddenly applied load. Now, what what is the work done when we apply gradually applied load? This is not W times delta there. This is rather in case of that gradually applied load, the work done in the case is U is or strain energy is equal to W by 2 times delta. This is what happened in the case of gradually applied load. Why was this? Because at a time t equal to 0, the load is 0 because initially the load was not there, right? So whereas at time t the load is W. So when you are taking load into consideration, you will be taking average load. Of course, there in the previous section when we discussed, we have used the integration process. Here W is W, right? But in this case, at time t equal to 0 or at time t equal to t, in both cases, load is W only because it suddenly came. There is no time gap. In both cases, W is W only. That's why the average load also becomes W. So average load times deformation is the work done. So you got that. So the strain energy developed by the body, this is same. Either it is a gradually applied load or it is a what you call suddenly applied load. Both cases it is same, right? So this you can even delta L because change in the length is a delta or delta L. So W times delta L is equal to half into R times delta L. Okay. So half into in this case also you can use delta L. Delta or delta L doesn't matter. If it is right delta here, you also can write delta because the length we have taken L, therefore it can be delta L. So now when you simplify, what you will get is R equal to 2W. So what is that meaning? The internal resistance is twice the applied load. So the amount of resistance developed is twice the applied. Now from the resistance, you can calculate the stress developed just by dividing the area of cross section. You will be getting the suddenly applied. What is the stress developed due to the suddenly applied load. So from this we can also infer that the suddenly applied load stress development is almost twice the stress developed due to the gradually applied, right? So I am concluding here about the differentiation. So what was the similarities here and differences we can find? Gradually applied load is, as I mentioned here, gradually when you apply gradually applied load, the deformation takes place gradually, and when you apply suddenly applied load, the deformation also happens suddenly. But in for both cases, the energy development, the internal resistance development will always be gradual only, right? So based on that, when you try to calculate the strain energy development due to suddenly applied load, you got the internal resistance is twice that of the load applied, and therefore the stress development due to the suddenly applied load is 2W by G, right? Which means that suddenly applied stress development due to suddenly applied is almost twice the stress development due to the gradually applied, right? So this is one part of our target. Now let's move on to the second one, which is strain energy due to the impact load. Before going that, let us look at a small numerical example to make it things clear. So here there was some information given asking us to find out what is the value of stress developed due to the suddenly applied load and as well as the deformation developed. Okay. So this is our unknowns. We have to find the stress development, that is sigma, right? And deformation, say delta L. These are the things that we need to find. So if you know the formula, you can easily find. Just now we have discussed this is nothing but 2W by A. Okay. then deformation in the of the rod is delta L. Okay. So what was the formula we discussed for this delta L? Right? It is nothing but strain. If you know strain, right? Or because here strain straight away you don't know because epsilon is not given here, right? But we may find out this in some other fashion because we know the stress, we know the Young's modulus, then we can find the delta L. Let's see how to proceed. So these are the things that are to be targeted. The number one is stress, number two is the deformation. So first of all, let us finish this. Right? For this, what was the information we require? We require the load that was given. See somewhere the load given. It was not given. It's given. Let's look at what was. Let us see what are the. No, we can just write down what are the things given. Water under a pressure of 6 Newton per mm square is suddenly admitted a plunger of diameter 100 mm. So there was a diameter of the pipe was given and the water pressure was given, right? The plunger is attached to a connecting rod of 25 mm diameter. So there was another is connected to another rod, right? That diameter was given. Now thereafter, and the pipe rod length was also given, right? So now, because we required W by A, 2W by A. So we require first of all W, what is the load acting. Load was not given, but instead the water pressure was given. So pressure times that area which it is carried, that will give you the amount of load happen. And then where we have to find the value of stress in the deform in the rod, we have to find. Therefore, we have to take the area of the rod. So first of all, what was the force acting due to water that we need to find out. So let us see what was the pressure was given. So you can note the pressure here. So that was the first information. Pressure, then multiply with the cross section area, you will be getting the amount of load that was acting due to the water, right? So plunger diameter was given, right? Plunger admitted on a plunger of 100 mm diameter. So diameter known means area we can find. So once you got the area, you can multiply that with the pressure, you got the force, that is the load onto the rod. Then diameter of the rod was given, then you can find out the area of the rod. Simply multiply, divide 2 times because sigma is 2W by A. So simply find out the value. So let's look at that solution. So 2W by A dash, where A dash is because we are supposed to find on the rod area has to be taken rather than plunge, don't take the plunger. So that's the value of the suddenly applied stress development due to suddenly applied load. Then finally, because we want deformation, we have the formula, right? Delta L is the strain, right? We have strain equal to delta L by L, and which can also be written as your sigma by epsilon. Sorry, E, Young's modulus. So you know all the rest of the things except this delta L. L is given to you. So multiply this L and you will be getting your delta L as sigma by E times L. That's all about the calculation of the deformation in the rod. Okay. So here, apart from this, the rest of the things are very quite simple. You maintain consistent units. This is actually mm square because pressure cannot be in mm cube. And consistent units are for the length and area units maintain mm square because the pressure was given in Newton per mm square. And then apart from that, I don't think any difficulties are here. You can get the values so easily. So there are some typographical error here, so you can note that. Fine. Let's go to the next one. Now we are going to entering into the topic of strain energy development due to the impact load. Fine. So whenever there is a load, now impact. What is impact load? When you are, usually, it was defined that what is impact load means it falls from a height, right? Like that we'll be saying, yeah, when something fallen from a greater height, it obviously will have some kind of velocity. So that's what here is. Whenever there is a load with some velocity acts on a body, it is said to be an impact or shock load. Not just no, it is no suddenly hit, but is coming with forceful. As previous case is slightly, it is coming suddenly, yes, but it may not have much velocity, but not only coming suddenly, but with great force, great velocity, it's coming. Such kind of loads we are referring here. That is impact load. No, an example can be kind of a blacksmith with a hammer. Some he will be beating in a different objects like steel specimens. He will be cutting off to make it a steel reinforcement, right? Making hooks and so on. Or sometimes he will be beating iron bars which was very much heated, and with the help of hammer he is striking it. So such a huge force that is. So that kind of loading that we are discussing here, impact load. So consider for that. Let's look at now what is the how to calculate stress in the members just subjected to the kind of impact loading. Right? Let's start. So we consider a rod. The rod has an area cross section A having a length of L, and at the end there was a collar attached to that. Right? To the rod there was a sliding weight attached here. Right? This can be moved to whatever way we want, and that was at present. Let's say there is at a height of h. Okay, the sliding weight was kept at a position h from the collar, right? And let's say after an instant of time, it was suddenly released. Then what happens? The collar will be subject to some kind of contraction or some kind of not contraction, I think, because it goes away, right? So it gets, let's say, the rod get extended, right? So the weight arrested by the collar produce an instantaneous del in the bar, right? So when it was dropped here, it will elongate the entire bar that we are seeing here. There it will be subject to some kind of extension because of the dropping of the sliding weight from a height. The whole thing is subjected to some kind of elongation. Okay. So this is the scenario of the loading, right? And there was a rod, then there was a collar attached to it, there is a sliding weight at a height h, and the length of the rod is L and the cross sectional area is A. At a particular instant, suddenly we release the weight and then it's hit the collar. As a result, there was a deformation in the rod by an amount delta L or dl, you can say. Now, let's say, no, let's consider the position of the equilibrium from the perspective that what was the energy lost by the weight and what was the energy gained by the bar. Let's look at from that perspective. Potential energy lost by the weight because it was dropped down from a height of h, right? So what was the energy drop? H, and because there was a what you call deformation happen in the process of after hitting the collar, that can be taken as delta L. Therefore, potential energy lost was this much, W times H plus delta L, where H is the distance between the sliding weight and the collar, and delta L is nothing but the deformation undergone by the rod. Okay. Now, strain energy absorbed by the bar, we know in terms of stresses, this is the formula sigma square or Fi square by 2E times volume of the bar. Let the volume, already we discussed area is A and length is L, therefore volume becomes AL. So let's keep it aside volume. So this Fi square by 2A, 2I, okay, or sigma square by 2A. If it is axial load, sigma square by 2. If it is shear load, tau square or Q square by 2E, like that, into volume. Right? That is the strain energy developed that we discussed in the previous section also when we are discussing about the strain energy development due to the axial and shear loads. Now for the case of equilibrium, the energy lost, total energy is conservative and if there is no loss of energy, ultimately therefore let's see the energy developed in both perspectives. So W times H plus delta equal to Fi square by 2I times AR. So simplification leads to this kind of equation. Fi square by 2E into L. This delta L, because I am interested to calculate stress, right? So let's transform this into the order of stress terms. We know delta L by L is strain, and strain I can written as sigma YE or Fi by instantaneous stress can be represented by Fi or sigma. It's up to your convenience which one, it doesn't make any difference, by X modulus. Because I wanted this quantity, bring out this term this side. So this is what will happen. Fi by E times L. That is your replacement of delta L. Once you got that, you get an expression like WH test WFIL by E by equal to Fi square by 2E times L. When you look at this equation, you can make a observation. This equation was a quadratic expression in terms of Fi's, just like ax square plus bx plus c equals 0, or x square plus some constant times x plus some constant is equal to 0. For such kind of equation, the solution comes by taking minus b plus r minus b square minus 4ac root over plus r minus root over b square minus 4ac by 2a. That was the solution. Now this particular what you call equation, now we will get rearrange the terms to get the quadratic expression. In the process, what will happen? Because I want to remove the quotient of this to making simplification, multiply the entire things with the reverse of this particular quotient. That means you multiply with 2e by a, then it get cancelled out and the other terms will be multiplied with this. So finally we will be getting this by multiplying the entire equation with this particular quantity. So we got this. Now the solution of that is simply minus b plus r minus b square minus put over b square minus 4ac by with 2a. The standard equation. Simplification of that results in the following equation. So here A is your quotient 1 and B is, when you bring this to this side, this becomes 2W by A, right? And your 4 is okay, A is 1 again, and this becomes minus when come to this side, so minus of minus becomes plus 2HEW by A upon simplification, right? So including removing that 2. So this is the final equation. Now once got this equation, we can bring out, we can make some suitable adjustment to bring out the common terms outside of the bracket. So for that, what I am doing is, here W square by A square is there. I want to get here also same term. So what I will do, I will multiply and divide the terms with the W by A, so that it becomes W by A times A plus A by W. This doesn't make the terms any change, because you can cancel out at any time. W W A. So upon simplification, rearrange the terms and bring out W square by A square outside. When the W square by A square comes outside, becomes W by A, right? Because it is a square term within the root. When come out, it becomes a normal term, right? From square term. So this becomes Fi equal to W by A plus W by A plus so and so. Here we don't consider the negative term because stress cannot be negative. Why stress cannot be negative? Because the kind of stress applied is created actually an extension. There is no question of deformation here. Therefore, instantaneous stress is given by W by A times 1 plus root over, not minus here, not plus or minus, it is simply only plus root over 1 plus 2 EAH or AEH. You can rewrite the terms as you are conveniently able to remember it. 2 AEH by LW or W. So, instant in elongation you want to simply multiply F5 with L. Okay. So, if H is very, which is 0, then it is come, that means the height was almost 0, then it is treated as a suddenly applied load. 2 is sudden load. Okay. Okay, let's look at the numerical example to get better picture of the calculation of the stress development due to impact loads. Here is a steel bar, 10 mm diameter, 150 centimeters long, stressed by a weight of 12 kgs, dropping quickly through a height of 5 centimeters before commencing to stretch the bar. Find the maximum instantaneous stress and the instantaneous alarm. So he is asking Fi or sigma I and what do you call it? Epsilon M, instantaneous elongation. Look at the given nodes. The diameter was given, area of diameter was given, then the length of the bar was given, height from which it is dropped is given, the falling load was given, Higgs quantities was given. Our task is this. So for which the formula we just discussed Fy or sigma I is equal to W by A times W by A times 1 plus root over 1 plus 2EH or 2AH 2AH by W L, right? What was that? Yeah, W L. This is the formulation. Oh, you know everything, just or not, we can just verify. W was given, darling load. Area you can find out because the diameter was given. So that's all. AEH. H is the from difference between height of 5 centimeters. Okay, so that 5 you can take and W anyway know, and L was also given, that was 150 centimeters. So straight away put in this formula. So that is W by A 1 plus root over 1 plus 2 AEH by yeah. Simplification of that results in this stress. Now if you want elongation in the bar, how do you find the elongation in the bar? You simply multiply F5 by E with L. Right? Previously also we discussed where is the yeah F5 by E to L. F5 by E into L. Now simplification of that, whatever things that we are supposed to calculate, this is the actual formulation. Now using that all values that are given, since we substitute, we will get the solution. Here FA by VE times L, that is elongation. So that's all the topic of the uh, discussion on the topic. Uh, um, Synergy due to axial and no suddenly applied load and impact loads. Right? Thank you very much for your patient hearing. Okay.